Hi folks, we're going to take a look at number 6 from the last lesson of the unit. So here it tells us that water runs into a conical tank at a rate of 0.9 meters cubed per minute. So then it gives us some information. I've already drawn the picture here. It tells us that it stands point down, so upside down, and has a height of 3 meters and a base radius. So you think of the base is, well, opposite to the tip. Here, base radius of 1.6 meters. And they want to know how fast is the water level rising when the water is 2 meters deep. All right, so we know that the water is being poured in, so that means obviously water is going to start rising. So I'm going to represent, at some random moment in time, the height of the water. Now you'll notice here that I didn't bother, I just basically drew a cross section of my cone just to make it a little easier. I could have drawn it to have a 3D look to it, but at some point the water just keeps rising. Now notice here I'm not going to input this particular piece of information because the water level is not fixed at 2 meters. This is just the water level at one particular moment in time. All right. So the information that I'm given in terms of what rate I know, it's going to be the volume because they're telling us that we're talking about the water that's running in. So filling it up, we're talking about the volume here. So I'm going to have to work with the volume equation of a cone. So the volume of a cone is given by 1/3 pi r squared h. So this part here should look familiar. It's just the volume of a cylinder, and cone with the same height and radius is just 1/3 of that. All right. So the issue with this equation is I know how to solve related rates equations with two variables. Okay, and so we definitely want v to be in there because they're giving me the rate of at which the volume changes, and I'm really only interested in the rate at which the height changes. So I really only want h in my equation. Now, just to give you a heads up that we could solve this with both equations, because if I take the derivative of both sides with respect to t, well, I could just use the product rule. But I clearly don't have enough information here to deal with both r and h being in the equation, because the only thing I'm interested in is the water level, which is h, and the only information I'm given has to do with the water level, again, h. So I'm going to have to find a way to get r out of this equation. Okay, and so this is where we're going to see yet another geometric tool that we can use. All right, because if I take a look at this height here, and I'll call this r the radius of the water, because the water itself is going to form a cone as it's rising, and I'll call this h the height of the water itself. All right, I see that I've got, a right angle triangle here where I'm interested in the two sides that are not the hypotenuse. Problem is I don't have any information about the hypotenuse, and I'm not particularly interested in the hypotenuse. So that takes Pythagoras out of the picture. All right. I also notice that there's no information about the angle here. Okay, so I'm probably not too interested in using trigonometry, but what I do notice is I notice two similar triangles. Okay, and as we've seen with other questions, similar triangles are a very useful tool in solving these equations. Okay, so what I'm going to do is I'm going to create I'm going to create a ratio using similar triangles. So if I take the height of the water, I'm going to compare that to the height of the whole cone. In other words, the length and the corresponding length in the larger triangle. So we have h over 3 is equal to r over 1.6, because this side of the triangle corresponding to this side in the larger triangle. So r over 1.6. Okay, now the question is which one of these should I isolate? Now normally I would say, well, isolate h so that I don't have to worry about squaring it. Okay, however, h is actually the variable I would prefer having in my equation because it's what I'm interested in and it's the information that I'm actually given. So even though I'm going to have to square it, I'm actually going to isolate r in this equation here. Okay, so since we're working with an application example, I'm not going to bother keeping things in in exact values. So I'm going to bring the 1.6 to the other side. So 1.6 divided by 3 is 0.53. Okay, so R can be written as 0.53 H. And now I'm going to substitute that into my equation. So what do we have? We have 1/3 pi times 0.53 H squared times H. So I'm just going to simplify this whole thing here. So I'm going to take my, so you can see it here. I'm going to take my 0.53 and I'm going to square it. Okay, and then I'm going to multiply it by pi and then divide by 3. Okay, and what do we have? We have 0.297. That's, pretty close to 0.3. Okay. So in the end, I'm left with 0.3, and h squared times h is h cubed. All right. So there's my equation that relates height to volume in this circumstance. But of course, I'm interested in the rate of change of height. So I'm going to take the derivative of both sides with respect to t. Okay, so dv dt is equal to the derivative with respect to t of the right-hand side of the equation, which is just 0.3 h cubed. All right, so here, what do we have? 0.3 is just a constant. All right, and since h cubed, this is going to be a composite function with respect to t, so I have to use the chain rule. So first I take the derivative of the outside function, which is 3h squared, and then I multiply it by the derivative of the inside function, which is just dh dt. All right, and now I have my related rates equation, and I can solve for dh dt because I know that the volume is increasing. Okay, now how do I know it's increasing? Because it's going into the tank. If this was a tank that was leaking water, well, I would be using a negative value for dv dt. But here the volume is increasing, so we just have 0.9 equals 0.3. And at the moment in time at which we're interested in is when the water level is exactly 2 meters deep. So there was a reason why they gave us that piece of information. All right, and now I can just solve for dh dt. Okay, and it should be positive since the water level is rising, so it's increasing. Okay, so let's see what we have here. We have 0.3. Actually, let's just start over here. So what do I have? I have 0.9. Okay, and I'm going to be dividing it by, and open up some brackets. So 0.3 times 3 times 4. Okay, and it looks like it's 0.25. So the height of the water is increasing at 0.25 meters per minute. Okay, since those were the units that were being used. All right, so let's just do a recap. So again, step number 1, get yourself a good diagram. Represent some random point in time where there's some water in the cone, okay, and realize that you have to work with the volume of a cone formula, okay, but because all the information given or of interest had to do with the height, we needed to find a way to get the radius out of the equation. And this is where we used another one of our tools, which was similar triangles, to set up a relationship between h and r. And once we have that, we can then take the derivative of both sides and find our related rates equation. Okay, that's it for this one.